So suppose we have two concentric semicircles connected on either side by a segment of wire. All right, this is a closed loop, so we can assume if we have a current flowing counterclockwise in the outer one, we have it going to the right in that one, clockwise in the inner semicircle, and to the right in that segment. Okay, so let's call them 1, 2, 3, and 4. Okay. If we want to find the magnetic field at point P due to this current, there's actually several contributions, right? We need to use Biot-Savart to find the contributions from 1, 2, 3, and 4. Okay? So, Biot-Savart, the form mu naught I over 4 pi times the integral of the ds vector crossed with r hat all over r squared, right? And even though this looks like a crazy intense integral, let's actually see how it's not really that bad. All right. All right. So segment by segment. So in section 1, let's do Biot-Savart for that. Integral. We'll see what our limits are shortly. The ds vector points in the direction of current. So let's say for 1 we go that way, right? That's our ds. And the r hat vector points in the direction, well, it goes from the segment of wire that's generating the magnetic field, and it points towards the point in question, so point towards point P. In other words, like that. From the wire to the point. So these are in opposite directions, so the angle in between is 180 over r squared. What's sine of 180? Well, that's just 0. So this whole term is 0, right? The contribution for B1 is 0. Looking across at 3, that's really similar to segment 1. For instance, we'd have a ds pointing to the right and also an r hat pointing to the right, right? That angle would be 0. So sine of 0 in that case would be 0 again. So for those two segments, Biot-Savart tells us their contribution is 0. So let's look at segment 2. For example, we might have a ds vector pointing at that orientation. The good thing about this integration is that we don't have to choose any specific ds along segment 2. Just pick one, and then we'll integrate its contribution along the entire length of the segment. And because this is symmetrical, that's easy. All right, so the r hat goes from that segment towards point P, and now that is a right angle. So the angle and this cross product is easy. We just have ds times the magnitude of 1 times sine of 90, also 1, over r squared, right? And actually, what's r squared? Well, r squared, the lowercase r, is the distance from the wire segment to the point in question, right? So it's the actual distance. In this case, I haven't specified it, but we'll call it r2. And while I'm at it, let's specify the inner distance of r1. All right. So that's r2 squared. And now let's do 4. Contribution from segment 4, the inner semicircle. Integral of ds. It's also sine 90, right? Because now for segment 4, ds points, say, that direction, and r hat going down, like that. So also sine. And the r is r1 now, squared. We need limits on both of these terms, on both of these integrals. So in B2, we're starting over here, and since the current's going counterclockwise, we're ending up exactly on the other side of that quote-unquote circle. So it's a distance of, well, half of the circumference. I'll call that S1, sorry, S2 for right now, and this S1. Okay, that's the arc length. So let's see. Let me pull out the prefactor, mu naught I times 4 pi, or over 4 pi, sorry. And we're integrating ds R2 is a constant, right? And we're going from 0 to S2. S2 is half of the circumference. So the circumference of a circle, well, is 2 pi r. So we have 2 pi r2, so therefore it's just pi times r2. Right? That's our upper limit. And then plus integral from 0 to, similarly for S1, it's 1/2 of 2 pi r1. That total hypothetical circumference. So this is pi r1, right? However, before I go on, we can't just go from 0 to pi r for both of them. The outer one, we're starting at, well, an angle of 0 and going counterclockwise to pi, right? Pi radians. The inner one, we're starting on the left where pi normally is, and we're going clockwise to where 0 normally is. So actually, we should switch these angles, or switch those limits. Okay, there. And now our integrands are like such. And now we can properly evaluate it. All right, so we have, let's see, well, that's easy. Integral ds is just, well, s. So that is pi times r2 over r2 squared plus, now we need to actually pay attention here. This is 0 minus pi r1 over r1 squared. Okay. Notice a factor of pi cancels out. We have mu naught over 4 times 1 over r2 minus 1 over r1. And this is our answer, right? And because the value for r2 is larger than r1, right, that means that this initial term, this 1 over a bigger value, will be a smaller number overall. So that means overall, this will be a negative direction, right? A negative value. So in that case, the magnetic field will point into the page, right? If you use the right-hand rule, the magnetic field from the outer R2 segment is coming out of the page. We can write that B field from 2 is coming out of the page. And the B field from 1 is going into the page.